Have you ever wondered what would happen if the Earth were to suddenly stop in its orbit and begin falling directly towards the Sun? How long would it take before the Earth was consumed? How would the temperature of the planet change? And would the Earth eventually be ripped apart by the overpowering gravitational influence of the Sun? Well, I recently came across an article by Atish Bhatia that sparked my curiosity. Could I work through the calculations to answer these questions for myself? Now, while this might sound like a sci-fi disaster scenario, it's actually a fascinating thought experiment that lets us apply fundamental physics principles. In this video, we'll explore how even basic physics can help us answer big questions about the universe. The video is structured in 4 parts. In the first part, we will estimate how long it would take the Earth to fall in a straight line into the Sun. In the second part, we will use basic thermodynamic principles to estimate how the temperature of the Earth would change as it fell ever closer towards the Sun. In the third part, we will estimate the point at which the gravitational force acting on either side of the Earth would be so large that the Earth would be ripped apart. And finally, we'll investigate how the Sun would appear in the sky as we fall to our inevitable fate. Before we begin, it's important to emphasise that this is purely a thought experiment. To make the problem manageable, we'll make several simplifying assumptions which we'll discuss throughout the video. Of course, in reality, there's no plausible way for Earth to suddenly stop in its orbit and fall directly towards the Sun. But for the sake of exploration, let's roll with this idea in the playful spirit it's intended. Even with these simplifications, there's plenty of fascinating physics to uncover, so sit back and enjoy the ride. Our first task is to estimate how long it would take the Earth to fall into the Sun. Consider the Sun and Earth separated by an initial distance of d meters at time t = 0. We'll also define the mass of the Sun as uppercase M and the mass of the Earth as lowercase m. As the Earth begins to fall, the distance between the Earth and Sun will change, and therefore we will label this distance as r of t to signify the distance between the Earth and Sun at time t. Now, before the Earth begins to fall at time t = 0, we are assuming that the Earth would be temporarily stationary with respect to the Sun, and therefore its initial kinetic energy would be 0. On the other hand, its gravitational potential energy would be equal to minus g big M little m divided by d, where d is the initial distance between the Earth and the Sun. Since the total energy is the sum of the kinetic and potential energy, it follows that the initial total energy of the system will be equal to minus gmm divided by d. Once the Earth begins to fall, it will gain kinetic energy, and the total energy at a distance r from the Sun will be the sum of the kinetic and potential energies at this distance, and will be equal to half m dr by dt squared minus gmm divided by r, where the first term represents the kinetic energy. If we then apply the conservation of energy, we can equate these two expressions, in which case we find the following blue expression. We can then cancel off the mass of the Earth from both sides of the equation, and if we then rearrange, we find the following expression. We can then rewrite the right-hand side in the following equivalent form. Finally, we can take the square root of both sides, in which case we find the following blue expression. We have taken the negative root because we expect r to decrease as t increases, because the Earth is getting closer to the Sun. Now, in order to solve this differential equation, we can rearrange and separate the variables, in which case we find the following green expression. And then, if we integrate both sides, we find the following yellow expression. So, how do we evaluate these integrals? Well, if we begin with the right-hand side, this integral is straightforward and simply integrates to the negative of the square root of 2gm divided by d multiplied by the time t, plus an integration constant which we've called a. So what about the left-hand side? To evaluate the integral on the left-hand side, we make a change of variables. we're going to let r equal d cos squared theta, in which case we see that dr by d theta is equal to minus 2d cos theta sine theta. And so we can then write dr equals minus 2d cos theta sine theta d theta. Next, if we sub this back into our integral, we get the following green expression. And if we cancel off the d terms, we find the following blue expression. Then, using the fact that sine squared theta equals 1 minus cos squared theta, we can simplify further, and when the dust is settled, we find minus 2d, the integral of cos squared theta d theta. To evaluate this integral, we use the fact that cos squared theta is equal to half plus half cos 2 theta, which means we can write the integral as minus d times the integral of 1 plus cos 2 theta d theta. If we then perform the integration, we find the following expression, where b is an integration constant. Finally, we use the fact that sine of 2 theta can be written as 2 times the square root of 1 minus cos squared theta times cos theta to rewrite our result in the following form. Now, if you recall, when we initially changed variables, we defined r as d cos squared theta, and so if we rearrange this, we find that cos squared theta is equal to r over d, and therefore cos of theta is equal to the square root of r over d. It then follows that theta is equal to inverse cos of the square root of r over d. And if we then sub this into our integral result, we find the following beautiful expression. We can then rewrite the second term in this expression in the following equivalent form. Okay, we're now in a position to combine our results. If you recall, we were trying to evaluate the following integral equation. We now have expressions for both the left and right hand sides, and so this equation takes the following form. Next, we can combine the two integration constants a and b into a new constant c, where c is equal to b minus a. In order to fix this constant, we can use the fact that when t equals 0, we know that r equals d, and if we sub this information into our equation, we find that 0 is equal to minus d times cos to the minus 1 of 1 plus c. And since cos to the minus 1 of 1 is equal to 0, we see that the constant c is equal to 0. And so we can now write our equation in the following purple form. Next, if we rearrange our equation for t, we find the following green expression. We can now use this expression to estimate how long it takes for the Earth to crash into the Sun. To do this, we're going to simply set r equal to 0. This is a slight simplification, since we are here assuming that the Earth and Sun are point masses, whereas we know that they have finite size. However, because the radius of the Sun and Earth are in general tiny compared with the distance between them, this turns out to be an exceptionally good approximation. And so we will proceed with this for now. If we then set r equals 0 in our equation, we find the following blue expression. And since cos to the minus 1 of 0 is equal to pi, we can write our time equation in the following form. And this simplifies to pi over 2 times the square root of d cubed divided by 2gm. Okay, so we now have an equation that tells us how long it would take the Earth to fall into the Sun. To find the exact value, we sub in the initial distance between the Sun and Earth, which is approximately 150 million kilometers, as well as the mass of the Sun, which we will take as 1.99 times 10 to the 30 kilograms. And if we plug in the numbers and constants, we find a value of 64.56 days. And so there you have it. If the Earth fell directly towards the Sun, we would have just over 2 months before we were completely consumed. We can visualize what's going on using a simple simulation. On the left-hand side, we see the Earth falling in a straight line towards the Sun, and on the right-hand side, we have time on the x-axis and the separation between the Earth and Sun on the y-axis. And we see that the line being traced out represents our time function at the top of the screen. Okay, so we've managed to derive an equation that predicts the time corresponding to a given separation between the Sun and Earth. So the next question is, can we use this equation to figure out when the Earth would pass through the orbit of Venus or Mercury during its fall into the Sun? If we plot our function with distance between the Sun and Earth in millions of kilometers on the vertical axis and time in days on the horizontal axis, we can then use the plot to estimate the time when the Earth passes the orbit of Venus and Mercury. The average orbital radius of Venus is 108 million kilometers, and if we read this off the graph, we find that this corresponds to a time of approximately 41 days. On the other hand, Mercury has an average orbital radius of 57.9 million kilometers, and if we read this off our plot, we find that this corresponds to an elapsed time of approximately 57 days. Okay, so we've figured out how to determine the time it takes to reach certain distances from the Sun during the freefall. So the next question is, what would happen to the temperature of the Earth as it fell towards the Sun? Now, to do this accurately is complicated, since there are several factors that need to be taken into account, ranging from the amount of solar radiation falling upon the Earth to the changing atmospheric effects of the Earth. For the purposes of this video, we're going to consider a very simplistic approach. However, it will still shed light on some of the major factors that determine the changing temperature of the Earth. Firstly, we will define the equilibrium temperature of the planet as the temperature at which the energy it receives from the Sun is balanced by the energy it radiates back into space. This temperature can be estimated using simplified models that account for various factors such as distance from the Sun, the albedo or reflectiveness of the planet, and greenhouse effects. Consider the Sun and Earth with a centre-to-centre separation of r. Next, let's call T subscript Sun the surface temperature of the Sun, and T subscript Earth the surface temperature of the Earth. How might we relate the surface temperature of the Earth to that of the Sun? To begin with, we can calculate the intensity of radiation emitted from the Sun, which corresponds to the energy emitted per second per square metre. To do this, we can use the Stefan-Boltzmann law, which states that the intensity is related to the fourth power of the temperature, where sigma is the Stefan-Boltzmann constant. To find the power output of the Sun, we then need to multiply the intensity by the surface area of the Sun, which means multiplying sigma T Sun to the power of 4 multiplied by 4 pi r Sun squared, and this simplifies to 4 pi sigma T to the 4 r squared. Now, the planet Earth will only absorb a small fraction of the total power emitted from the Sun. To find out how much, we can calculate the power per unit area by imagining that at a distance r from the Sun, this radiated energy is spread over a sphere of surface area 4 pi r squared. It then follows that we can write the power per unit area at this distance to be equal to the power of the Sun divided by 4 pi r squared. And if we sub in the expression we derived for the power, we find the following purple expression, and this simplifies to sigma T to the 4 r squared divided by little r squared. Okay, so we now have an expression for the power per unit area, and it follows that the power incident on the surface of the Earth will be equal to this expression multiplied by the cross-sectional area of the Earth. If r subscript Earth is the radius of the Earth, then the power received at the surface of the Earth will be equal to the following blue expression, where pi r Earth squared is the cross-sectional area of the Earth. And we can then rewrite this in the following form. Next, if we assume for the moment that all of this power is absorbed, then we can write the following equation for the power absorbed by the Earth. However, we know that in reality, not all incident radiation is absorbed, and this is because some of the radiation is reflected by the surface of the planet. The fraction of incident radiation that is reflected back into space from the surface of a planet is known as the albedo of the planet. It's a dimensionless number between 0 and 1. A higher albedo means more reflection and less absorption, and a lower albedo means less reflection and more absorption. It then follows that the fraction of power absorbed by the Earth will be equal to 1 minus A. We can then represent the amount of power absorbed by the Earth's surface on our diagram. Next, if we assume that the planet is in thermal equilibrium, it should be true that the total power absorbed by the Earth is equal to the total power emitted back into space from the surface. And we can calculate this emitted power using the Stefan-Boltzmann law. If the temperature of the Earth is T Earth and the radius of the Earth is R Earth, then using the Stefan-Boltzmann law, we can say that the power emitted from the surface of the Earth will be equal to the surface area of the Earth multiplied by sigma T Earth raised to the power of 4. And assuming thermal equilibrium, these two power relations should be equal to each other. And so we have the following equilibrium condition. We can then rearrange this and we find the following yellow expression. If we then take the fourth root of both sides of the equation, we find the following equation for the temperature of the Earth. If we then sub in the radius of the Sun and set the distance between the Earth and Sun to be 150 million kilometers, and the surface temperature of the Sun to be 5,778 Kelvin, then we find that the predicted temperature of the surface of the Earth is 255 Kelvin, which corresponds to minus 18 degrees centigrade. Now, this is clearly lower than expected, and this is because we have used a very simple model. In our analysis, we have neglected the Earth's atmosphere, whereas in reality, we know that the Earth's atmosphere absorbs and re-radiates energy. So let's see how we can build this into our model. Let's then consider a very simple approach in which we model the atmosphere as a single layer which can absorb and re-radiate energy, both into space and back towards the Earth's surface. A fraction of the shorter wavelength visible light incident on the atmosphere will pass through the atmosphere and be absorbed by the Earth's surface. Longer wavelength infrared radiation will then be emitted by the Earth's surface upwards. Some of this will be absorbed by the atmosphere and then re-radiated back towards the Earth's surface, and some will be absorbed and then re-radiated into space. Now, we can quantify all of this as follows. Firstly, we've already seen that the power incident on the Earth from the Sun is given by the following expression. And furthermore, we have seen that only a fraction of this, determined by the albedo of the Earth, will end up getting absorbed by the surface. Next, we can use the Stefan-Boltzmann law to say that the power emitted from the Earth's surface will be equal to the surface area of the planet Earth multiplied by sigma times T Earth raised to the power of 4, where here T Earth is the surface temperature of the planet. Now, in our simple atmospheric model, this radiation will then be absorbed by the atmospheric layer, and then some of this will be re-emitted into space, and some will be re-emitted back towards the Earth's surface. And so we can write that the power emitted in either direction by the atmosphere will be equal to the surface area of the atmosphere multiplied by sigma times Ta to the power of 4 multiplied by epsilon, where Ta is the temperature of the atmosphere, and epsilon is a measure of how effectively the atmosphere absorbs and re-emits infrared radiation. You can think of epsilon as indicating the infrared opaqueness of the atmosphere. A value of epsilon equals 1 would mean that the atmosphere behaves like a perfect black body, completely absorbing and re-radiating all infrared light that hits it, while epsilon equals 0 would mean that it's transparent and does not interact with infrared light at all. We can then use the conservation of energy and say that if the planet's temperature is to remain in equilibrium, then the power incident on the Earth's surface, which is due to the following two terms, must be equal to the power radiated from the surface. It then follows that at the surface of the planet we can write the following relation, and if we rearrange this and simplify, we find the following relationship. Next, if we consider the atmosphere itself, then for the atmosphere to be in thermal equilibrium, it should be true that the power absorbed by the atmosphere should be equal to the power emitted. And hence we can write the thermal equilibrium condition of the atmosphere in the following form, and we can then combine the terms on the right hand side. Then, if we simplify, we find the following relation that relates the temperature of the Earth's surface and the temperature of the atmosphere. Next, we can combine this with the other equation that we derived, which related the surface temperature of the Earth with the surface temperature of the Sun, and we can substitute the one into the other, in which case we find the following yellow equation. Next, we can rearrange this slightly, and then write an expression for the fourth power of the Earth's surface temperature. And then finally, if we take the fourth root of both sides, we find the following equation for the temperature of the Earth. We can see that this is a function of the surface temperature of the Sun, the radius of the Sun, and the distance between the Earth and the Sun, as well as the Earth's albedo and the infrared opaqueness. Okay, so we now have an expression for the temperature of the planet using our crude single-layer atmospheric model. So what does this predict for the surface temperature of the Earth? Well, we know that the surface temperature of the Sun is around 5,778 Kelvin, the radius of the Sun is around 6.96 times 10 to the 8 meters, and the current average distance between the Earth and Sun is around 150 million kilometers. We also know that the Earth has an albedo of around 0.3 and the infrared opaqueness is around 0.78. So if we plug these numbers into our equation, we find that the predicted surface temperature is now 288 Kelvin, which is around 15 degrees centigrade, and this is in fact very close to the average surface temperature of the Earth. So we see that our crude atmospheric model has significantly improved our predicted temperature. Now, if we look at our surface temperature equation, we see that it's a function of the distance between the Sun and Earth. If we sub in all the constants, then we can write this simply as 1.12 times 10 to the power 8 multiplied by 1 divided by the square root of r, where r is the distance between the Earth and the Sun. We can then use this equation to estimate the temperature of the Earth at different distances r during its fall into the Sun. Furthermore, for each different distance r, we can figure out when this will occur using the equation that we derived earlier for the time. If we then combine the temperature and time equations, we can then predict what the surface temperature of the Earth will be at different times during the Earth fall, and we can plot the results in a graph, with time on the x-axis and temperature in Kelvin on the y-axis. We can see from the plot that the temperature increase is actually very slow, with only a rapid increase occurring within the last few days and hours of the Earth's fall into the Sun. If we zoom in a bit and change the temperature scale to centigrade, then we see that during the first 60 days of freefall, the temperature increases by around 300 degrees centigrade. And we can then use this plot to read off some critical temperature values during the Earth's fall into the Sun. For example, during the first 20 days of freefall, the Earth experiences only a gradual warming, but by the 30th day, the average temperature reaches around 37 degrees centigrade, ushering in severe heat waves across the globe. As the Earthfall continues, the Earth warms to around 60 degrees centigrade by the 40th day, presenting dangerous heat levels that pose significant risks to all forms of life and the natural environment. At 50 days, the heat intensifies further, with temperatures climbing past 100 degrees centigrade and the oceans start boiling and the atmosphere becomes saturated with steam. By day 60, the situation grows even more dire as the temperature reaches over 270 degrees centigrade, leading to the complete loss of liquid water due to the total vaporization of the oceans. If we zoom in from day 60 onwards, the escalation continues. By day 62, temperatures reach 370 degrees centigrade. By day 64, temperatures hit 790 degrees. Rock minerals soften and partially melt, triggering widespread volcanic activity and further weakening the crust. By day 64.5, as Earth plunges closer to the Sun, temperatures pass 1,700 degrees, melting vast portions of the crust into a planet-wide magma ocean. the last remnants of Earth's atmosphere are stripped away by intense solar radiation. At day 64.55, temperatures exceed 3,500 degrees centigrade, vaporizing the planet's outer layers. The once solid world collapses into a superheated cloud of molten silicates and metal vapors. Even the iron-nickel core liquefies and begins to vaporize. The Earth is now dead, a disintegrating shadow of its former self. Within moments, it will be completely engulfed by the sun's photosphere, its atoms dispersing into the inferno of the star that once gave it life. Okay, so this all sounds very dramatic, but the drama is not over. Our next task is to determine when the Earth will rip apart. So let's do that. Because one side of the Earth is closer to the Sun than the other side, the gravitational force acting on the near side will actually be larger than on the far side. And this difference in force is known as the tidal force. We can estimate this difference by multiplying the mass of the Earth by the change in gravitational field strength between the near side and far side of the Earth. And if you recall, the gravitational field strength at a distance r from the Sun will be given by the following equation: G equals big G big M divided by r squared, where M is the mass of the Sun. To get a sense of how the gravitational field strength varies with distance from the Sun, let's plot the field strength at a distance of 700,000 kilometers to 1.3 million kilometers from the center of the Sun. We see that the curve follows a classic inverse square law relation. Next, if we shade a region on our graph with a width equal to the diameter of the Earth, then we see that the diameter of the Earth is much smaller than the range of distance values that we're considering. Furthermore, by drawing a tangent to the line at the location of the Earth, we observe that the field strength varies in an approximately linear fashion over a small region equal to the Earth's diameter, with the tangent providing a reasonable approximation to the curve in this local region. We can see this even more clearly if we zoom in on our graph. Because the change in field strength appears linear within this region, we can say that the gradient, delta G divided by delta R, is roughly equal to the instantaneous rate of change, dg by dr, because the curve is nearly straight in this small region. From this perspective, it follows that we can write delta G as approximately equal to dg by dr multiplied by delta R. Now, if we're only interested in the magnitude of the change in field strength, then we can write this as delta G is approximately equal to the magnitude of dg by dr multiplied by delta R. And so we see in our diagram that delta R is equal to the diameter of the Earth, which is simply twice the radius of the Earth. It then follows that we can write delta G as approximately equal to the modulus of dg by dr multiplied by 2 times the radius of the Earth. We can then use this expression for the field strength to calculate the derivative of the field strength with respect to r, in which case we find the following expression. If we then take the modulus of this expression, we find 2gm over r cubed. And then if we sub this into our equation for delta G, we find the following yellow expression. We can then use this to estimate the tidal force, which is approximated by delta F being equal to m times delta G. And if we sub in our result for delta G, we find the following purple expression. And this represents the tidal force acting on the Earth at a distance r from the Sun. Okay, so the question we now want to answer is, could this tidal force rip the Earth apart? And this leads to the natural question, what is holding the Earth together in the first place? Well, the answer to that is gravity ultimately binds the Earth together. Every little bit of mass within the Earth gravitationally attracts every other bit of mass, and the net effect is a gravitationally bound object. We can estimate this gravitational binding force by splitting the Earth into 2 hemispheres, each with mass m over 2. As a first order approximation, we assume that the centres of mass of these hemispheres are separated by roughly the radius of the Earth. In that case, we can use Newton's law of gravitation to estimate the binding force which will be equal to g times m/2 squared divided by the radius of the Earth squared, and this simplifies to gm squared divided by 4r squared. Now, if the tidal force that we derived earlier exceeds the planet's self-gravitational binding force, then the planet will be torn apart. In other words, when delta F is greater than F bind, the planet can no longer hold itself together by its own gravity. To estimate the critical distance when this occurs, we set the binding force equal to the tidal force, in which case we find the following expression. Next, if we rearrange for r cubed, we find the following blue expression. We now want to rewrite this in terms of the density of the Sun and Earth. To do that, we recall that the density is defined as the mass per unit volume according to the relation ρ equals m/v. And if we rearrange this, we find that m is equal to ρ times v. Then, assuming that the Earth and Sun are spherical, we can write the volume as 4/3 pi r cubed, in which case the mass can be written as m equals 4/3 pi r cubed times the density ρ. If we then apply this to the mass of the Sun and Earth, we can rewrite our expression for r cubed in terms of the density of the Earth and Sun. If we then take the cube root of both sides of this equation and simplify, we find that the critical distance is estimated to be 2.52 multiplied by the radius of the Sun multiplied by the cube root of the density of the Sun divided by the density of the Earth. This provides a basic estimate, but a more precise calculation of the Roche limit, the minimum distance at which a celestial body held together by self-gravity will disintegrate due to tidal forces, requires considering the deformation of the Earth and correctly accounting for its mass distribution. One approach is to model the planet as a liquid. The full calculation is complex and does not yield an exact algebraic solution, but Edouard Roche derived the following widely used approximation. If we use this more sophisticated result and plug in the average density of the Sun and Earth, we find that the Roche limit for the Sun-Earth system is approximately 1 million kilometers. Now, given that the radius of the Sun is just under 700,000 kilometers, the Roche limit critical distance for the Earth is only just over 300,000 kilometers above the surface of the Sun. And to put this scale into perspective, this is what the planet Earth looks like next to the Sun at this distance to scale. So, our next challenge is to determine when the Earth will cross this point and what the surface temperature will be at this stage of the Earth's fall. To answer these questions, we can refer back to the equations that we derived earlier. Firstly, if we sub the Roche limit into the time equation, we find a value of 64.546 days, which is literally a matter of minutes before the Earth would hit the surface of the Sun, the photosphere. At a distance of just over 1 million kilometers, we can then use the surface temperature equation we derived earlier, and we find a value of 3,412 Kelvin. At this temperature, rocks would melt, and the fluid approximation that underpinned Roche's formula is a reasonable assumption. Okay, so let's take stock. So far, we've explored how long it would take for the Earth to fall into the Sun, how the temperature would change along the way, and at what point the tidal forces would become strong enough to rip the planet apart. Our final step is to consider how the Sun itself would appear in the sky as we plummet towards our inevitable fate. Specifically, we want to calculate how the angular size of the Sun changes as our distance to the Sun decreases. To answer this question, we can draw a diagram of the Earth-Sun system. It's clear from the diagram that if we draw two lines from the Earth to either side of the Sun, we can make a triangle. And if r is the distance between the Earth and the Sun, and r subscript Sun is the radius of the Sun, then we can write the angle in each right-angled triangle as θ/2, where θ represents the total angle subtended by the Sun. We can then use simple trigonometry to write tan of θ/2 is equal to r Sun divided by r, and this implies that theta over 2 is equal to arctan r sun divided by r, and therefore we can write theta as 2 times arctan r sun divided by r. We can then use this equation to find the angular size of the sun in the sky at different times and distances. For example, it would take until day 50 before the angular size of the sun roughly doubled. By day 60 it would have doubled again. Then at day 64, at a distance of 11 million kilometers from the sun would have an angular size of just over 7 degrees. And then just half a day later, the angular size would jump massively to 26 degrees, dominating the view from the molten, vaporizing Earth. Okay, so let's end with a little bit of light-hearted fun. Let's imagine that the Earth was somehow resilient against change as it fell into the sun. And let's imagine what the sun would look like at various stages during the final fall. At 63 days, the sun appears large in the sky. At 64 days, it dominates, gently beckoning the Earth. And then, at 64.5 days, it's all we can see. Our fate is sealed. Thank you for listening, and until next time.